Hi there, Luke McKinney, Prep 101's Physics 1D03 instructor. In the last video we looked at the laws and diagrams for forces. In this one we look at the specific forces and the tips that'll make them easier to deal with.
The first force we look at, and definitely the one with the most wide-scale effects in our universe, is weight, due to the force of gravity. But before we dig into that, we have to look at the words, because there's a couple of important words here: mass and weight. Now, in conversational English, those get very mixed up. They're all sort of jumbled together. But in physics, there is a clear difference between them. So we need to be aware of that. This is, in fact, the last scalar vector pair that we need to be aware of. Mass is a scalar. You can just have a bag of 1 kilogram sugar, and that's just a number. And anywhere in the universe, that'll be the same number. It's a property of the bag. It's got 1 kilogram. A vector, however, on Earth, that 1 kilogram of sugar will feel a force of 9.8 newtons down towards the center of the Earth. So that is a vector. That depends on a number. And that also depends on the Earth. It can change. If you were on the moon, that would only be maybe 1.6 newtons. If you were above Jupiter, if you were close enough, it would be much bigger. If you're floating in space, you might have no weight at all. And that's, for example, if you had a sumo wrestler in deep space, they would be weightless. They could float, but they still wouldn't make a good astronaut because they still have that gigantic mass. So it would still take a large force to accelerate them around the place, because the mass is a measure of how hard you are to accelerate, as we saw before. So what is the weight? Well, the weight, or the force of gravity, whatever you want to call it, is the mass times the acceleration due to gravity. And we saw before, the acceleration due to gravity is 9.8 meters per second squared down. So that is that. Now, you'll notice there, mass and weight have different units. So you'll want to watch out for that when people mention it, because they'll just say something like a 50 kilogram box. Well, if that's 50 kilograms, then the mass is 50 kilograms. And the weight, we'd have to work out by multiplying by g. So that's 50 times 9.8 is 49 newtons. But if a problem says a 600 Newton box, that's newtons, so that's already weight. So we know the weight. And if we wanted, we could then work out the mass by plugging in g and going through that there. So that's very common. Now, there's one common example of this that's useful as a wee shortcut for me to give you, because it makes your life a lot easier there. If I have something in free fall, I know it feels the weight force of mg down, and it'll just fall with that acceleration. But if we have a block on a frictionless slope, it'll feel a weight straight down, but it can't actually move down. It could only move along the slope. So this is a case where we would very often take tilted axes. We'd have a tilted x-axis along the slope and a tilted y-axis perpendicular to the slope, because then it'd be much easier to calculate the accelerations. So we want to break up this weight into components. Now we can go through the whole trigonometry of it if you want, and I'll show you that in a bit because some people want to see it. But we can just say, we know that's going to break up into an x component and a y component. And we know there's going to be a cos and a sine in there, because that's how you break those things up. So here's the simple way. We just remember that sine slides down the slope. Sine slides down the slope. The only physics tip that can be said by a snake. I used to make a Harry Potter joke now, but seems to be falling out of fashion now. So what's the other one? Well, then the other one is cos, that way. cost crushing the slope, if you like. Now, sometimes people want to know, okay, look, how did you get that shortcut? So of course, I'll show you that. We have a slope, an angle theta, and we have the weight acting straight down. And we want to break that up into a component here. So this is a right angle, and this one here is a right angle. Now, we know in any triangle, there's 180 degrees. So this 90 degrees, this, and this other angle, let's call it phi, must equal 180 degrees. But, change color to show it, this is also a triangle. So this, and this angle must also be 90 degrees, add up to 180 degrees. And so this must be the same angle. Again, you'll never be asked to derive something like that, but when I say a little shortcut, some people always want to see where it comes from. So that's that. And now once we know, we have the hypotenuse and the angle, then the opposite side is just the hypotenuse times the sine of the angle. And that can be used to find the component of the force along the slope. And you'll find that's very useful when doing problems and exams with that force there. So where does this G come from? We know the weight, or the force of gravity, is the mass times the acceleration due to gravity, but that's only near the surface of the Earth. The actual gravity force between any two objects comes from the law of universal gravitation, which is no worries to us because it's always on the equation sheet. The universal constant, G, mass 1, mass 2, over the distance between their centers squared. Now, G is just on the equation sheet, 6.67 by 10 to the minus 11 Newton meter squared per kilogram squared. Now there's something about this one to watch out for. This distance has to be the distance between the centers of the objects. So if you have a planet and a moon, you have to make sure the distance is the distance between their centers. But if we're just talking about a little person on the surface, we don't worry about it as much. So it's just from the center of the Earth up to the surface. In fact, this is something that happens quite a lot. We often talk about things on the surface of the Earth, so the radius is always pretty much the same. The mass of the Earth is always pretty much the same. And the universal constant of gravitation, well, I'll let you guess how often that changes. So we gather all those together. Mass of the Earth, radius of the Earth squared, and we just call those G, the acceleration due to gravity near the surface of the Earth, which we know to be 9.8 meters per second squared. And you can see there's a potential question there. You can work out this G for any object. You could work out G for Jupiter, on top of a black hole, over the moon, just by plugging in the mass and the radius of those objects. And then you could use that new G in all of the equations we've seen G in, just for that planet there. The next force we look at is the normal force. We just saw weight, and if I have a weight force of 800 newtons down, why am I not currently accelerating down? Because we know forces cause acceleration. It's because of the normal force. I'm touching the ground and there is an upwards normal force cancelling out the weight. So actually the sum of all the forces on me is 0. So I'm not accelerating, I'm in equilibrium. This normal force, it's called normal because that's another word for perpendicular, or it's at 90 degrees to whatever surface I'm on. And this also leads to a nice keyword. If I look at the forces acting on me, I know The sum of all the forces acting on something is the mass by the acceleration. Well, I have plus the normal force up minus my weight of 800 down is equal to the mass times my acceleration, which is 0 because I'm just standing there. So the normal force minus my weight is 0. So the normal force equals my weight. And that happens a lot. Not every single time, but a lot. So often it actually becomes a keyword. When questions ask about your weight, that's the weight force we just saw, the mass times the acceleration due to gravity. But when they mention something about your apparent weight, or what weight you feel, then that's asking about the normal force instead. The reason being, your body can't actually feel its own weight force acting down. Your body, as an instrument, can only really feel things that happen to it or that are done to it. So it feels the normal force pressing up on it. And because that's usually equal to your weight, over time we've learned to associate that with weight. And that's why if the normal force changes, you can feel heavier or lighter for a second. You might have experienced this, for example, on a roller coaster, on a car going over bumps, or in the most famous example, in an elevator. If I'm standing in an elevator that's accelerating upwards, that means I'm accelerating upwards. So if I draw my free body diagram, I have my weight down, the force of gravity on me. I have the normal force up, perpendicular to the floor of the elevator. And the sum of all the forces is equal to the mass by the acceleration. And remember, in y, up is positive, down is negative. So I've plus the normal force up minus the weight down is equal to the mass by acceleration. So the normal force, my apparent weight, is my actual weight plus the mass times the acceleration of the elevator. So you can see if the elevator is accelerating up, so that's positive, the normal force will increase and I'll feel heavier. If the elevator is accelerating downwards, and then the acceleration would be negative, because remember, in physics, plus and minus are just directions, then the normal force would reduce and I would feel lighter. But this only happens when you're accelerating. So we revise an old keyword. If somebody instead says we're at constant velocity, remember constant velocity means the acceleration is 0 and we get back to the normal force just being equal to the weight again. Now this normal force, sometimes also called the contact force, and that's because it happens anywhere two things touch. One example, if I was on a slope, so I'm standing here, my weight is still straight down, but the normal force is perpendicular to the slope. So those don't exactly cancel out anymore. In fact, I can do it in a bit more detail. We've seen how to break up the weight into components. So if I break the weight up into the sine component, sliding down the slope, and the cos component, crushing into the slope, we can see what happens here. The normal force and the cos component can cancel out. So I don't accelerate through the slope. You might have noticed this. It's not like a video game where you can suddenly go through the scenery if you're moving fast enough. More interestingly though, there's nothing to cancel out this sine slides down the slope. And I will in fact start to slide down the slope if it's a very icy, slippy hill, if it's smooth and there's no friction. If there's friction, that could stop us, and we'll look at that later. Other important examples, if you have a ladder leaning against a wall, well, it's not going through the floor, so there's a normal force with the floor, and it's not going through the wall, so there's a normal force with the wall. And you see at each point, it's at 90 degrees, and you definitely want to write both of those on your free body diagram so you don't miss one out in the equation. Another interesting case is where you have multiple blocks stacked on top of each other or beside each other, because they will exert a normal force on each other. If I look at A will feel its weight down, the mass of A times the acceleration due to gravity, and the normal force between A and B up. And you'd always look at the furthest out block first because it's got the least going on. Now, if that's just sitting there, the sum of all the vertical forces on A is 0 because it's not going up or down. So you've plus the normal force up minus the weight of A down is 0. So the normal force is the weight of A. Then you move on to block B. So B has its own weight acting down, the normal force between B and the ground acting up. And if B was sitting there on its own, that's all that would be happening. But remember, A is touching it from above, so there's a normal force between them. And we have Newton's third law. If the normal force between A and B is pushing up on A, then it must be pushing down on B. So the normal force between A and B is pushing down. So you can see that's how the weight of A will affect B, because it's pushing down on it. And then the sum of all the vertical forces on B is 0, plus the normal force between B and the ground up, minus the weight of B down, minus the normal force between A and B. And notice how that's way easier to follow and to work with than just saying NBG minus MBG minus NAB. Like, that sounds like somebody very confused about sports leagues and just not doing a good job of pretending that they know what they're talking about. So we plug in what we know. You always do equations one step at a time. And then we can see the normal force between B and the ground is the weight of B plus the weight of A, as we'd expect. So if there was a scale or a weight measurement device underneath B, the force it would read would be this normal force. That's another way they can. The next force is the force of tension. Again, not tension as we'd say it in conversational English. We all understand that feeling already. But in physics, now in physics, the force of tension is the force in a rope or a cable or a stick that you're using to pull something. And there's a couple of things about this. The first is the tension is the same everywhere in the same rope. And the tension is always pulling. So what do I mean by that? Well, let's say we have a slope with two blocks, A and B, connected by a rope. Now, if they are connected by the same rope, that means there's the same tension everywhere in that rope. So if I was to look at A just on its own, it'll feel a tension pulling up in the direction of the rope. If I now look at B on its own, it will feel the exact same tension pulling in the direction of the rope. So that's down the slope now. And it'll always be like this. And it doesn't matter what blocks A and B are doing. If they're just sitting there, if they were being pulled up the slope, if they were sliding down the slope, it doesn't matter what direction things are moving in. The tension is the same everywhere in the rope, and it's always pulling on the object. And that's very useful for solving problems with these. You just look at the simplest block first, find the tension, then you can plug it into all the others. Now, what do I mean by simplest? That's not a great word to be throwing around for problems, but it actually works because it's just whichever block has the fewest things going on, the fewest things connected to it. There's another effect of ropes. Things on the same rope move the same amount. And that means they have the same speed and the same magnitude of acceleration. Well, what do we mean by that? Well, if we look at A and B here, we can see if B moves up 1 meter, A must move up 1 meter, and so on. But it's not always in the same direction like that. A classic example, if we have two more blocks, C and D, we can see now, if C moves 2 meters to the right, D will move 2 meters down. So they move the same distance, the scalar amount, but the vector, the displacement, is different. So we just remember to take account for that when we look at it. So we can see if C had a speed of 2 meters per second to the right, a speed of 2 meters per second, so a velocity of 2 meters per second to the right, then D has a speed of 2 meters per second down, turning it into a velocity. And likewise for accelerations, if C was accelerating 3 meters per second squared to the right, then D would be accelerating 3 meters per second squared down. So C's horizontal acceleration is +3, whereas D's vertical acceleration is -3. So you can see diagrams help a lot with this. You just break things up and step through them one step at a time as you do them. There's a bunch of different exam problems that use different arrangements for these, good for practicing those. Other condition about tension, the minimum tension in a rope or anything is 0 newtons. And this is often called the rope going slack, or it's about to go slack. So the tension can never be negative, because then you'd be pushing things instead, and then you don't have a rope, you just have a stick, which is different. Other than that, sometimes they'll tell you the maximum tension in a problem, which is a breaking tension. So they say, oh, the tension in this rope can go up to 400 newtons. So then you would just say, okay, that's the value of tension. Let's see what that gives me there. Now, tension is also useful in pulleys that let us lift heavier objects. So let's have a look at one of those. We have a roof, and we have a pulley connected to a big mass. And we set our pulley up to be pulled by a force, to be lifted actually by another mass. So we have a single rope going along here, and this shows how pulleys can be used to multiply forces. So let's tidy that up there to make it explicitly clear that's vertical. Seamless editing there, as you can see. So this system is in equilibrium. State M large in terms of small m. Well, you get a thing like that, you just break it up into words. Equilibrium means the acceleration everywhere is 0, which means the sum of all the forces everywhere is 0. And we've got masses, so we know we have weight, and we have a rope, so we know we have tension. So this becomes a forces thing. So we look at the free body diagram. First, we look at this little block on its own. You always break things up on their own. So you have a mass with a weight down and the tension pulling up. So the sum of all the vertical forces are 0 because it's an equilibrium. We were told that. So you've plus the tension up minus the weight down is 0. So the tension is the weight. So we're definitely halfway through now. That's not what we're asked, but we found something out. And that always means we're halfway through. So what do we look at next? Well, next, we look at how the big mass is connected to the same rope. So we look at this. And so we have the big mass connected to the pulley, and it has the big weight down, a tension up here, and a tension up here. Because remember, the tension pulls the same everywhere in the rope. So if we have a rope here pulling up, the tension is pulling up. The rope here is pulling up. The tension is pulling up. This is where sometimes people outsmart themselves. They think, oh, but if this is going around, isn't one up, one down, all the rest? No, remember, it doesn't matter. For one thing, in this system, it's in equilibrium. They're not moving anyway. And even if they were, even if the rope was threading down around that pulley, when we looked at it, it's always pulling in the direction of the rope. So let's look at that. The sum of all the vertical forces here is 0. So much clearer than sigma Fy equals 0. So you have plus a tension up, minus the big weight down. So twice the tension is equal to the big weight. So that's twice the small weight is equal to the big weight. So we can cancel out the g's. And we find the large mass is twice the small mass. So a small mass can lift twice as big a mass, and you go, wow, that's pretty effective, which is fun. And sometimes people get a bit, hang on, we can just multiply masses and weights like that? Not really, because this small mass can hold up a weight twice its mass with 2 ropes. But if we want to lift this mass by 1 meter, there's 2 ropes there, so we'd have to pull this one down by 2 meters. So there's a balance there. Although things sometimes people get worried about, think, well, hang on, how can both of these be pulling up? Well, remember, it's because ropes are always pulling. So if we cut that from the other side, and we just looked at the rope coming down from the roof and the rope going up to the other pulley, from the top side, we'd see those tensions are always pulling down. So remember, wherever you cut a rope, it's always tension and it's always pulling in the direction of the rope, which is fun. The next force is the spring force. The spring force is the cranky sleeper of the forces. Whatever you do to it, it's like, no, stop, let me go back to where I was. If you stretch a spring, it'll pull in, trying to get back to the length it was. If you squeeze the spring, it'll push out, trying to get back to the original length it was. In both cases, it's trying to restore. So it's a restoring force because it's trying to restore itself to the original length. Now, a cute little note here, sometimes people miss, you'll notice these forces happen at both ends. So don't miss that should it come up. It's like you might only be pulling it at one end, but the resulting force will be exerted at both ends. The formula for this is the spring force is minus the spring constant times the change in length of the spring. And you're definitely going to be wanting to say these out in words. Because if you just say Fs equals minus Kx, well, x just looks like a regular distance. But this distance x is the change in length of the spring. And that's the change in length of the spring from unstretched. For example, let's say a 10-meter spring is stretched to 11 meters. what is the spring force? And K is 10 newtons per meter. Now, if you're just saying Fs equals minus Kx, x, that's a distance. So you're looking for a distance, 10 or 11. And of course, both of those are wrong. Here you want the change in length of the spring. So the change in length is the new length minus the old length, which is 1 meter. And then the size of the spring force, you can go through the whole formula if you want. Fs is minus 10 times 1 meter, which is minus 10 newtons. So that'll be 10 newtons trying to contract the spring because it's opposite to the stretch. But you don't often have to juggle these things around. And sometimes people sort of trip themselves up by plugging in that minus and accidentally reversing the direction of the spring. So a useful thing I often do is I get the magnitude from the math and the direction from the diagram. What do I mean by that? Well, I mean like I can just find the size of the spring force is just the size of the spring constant times the change in length of the spring. And then I just know how big the spring force is. Half the time, that's all we need. But if I need to find its direction, well, if I have a block squeezing a spring, I know if that block spring is being squeezed, then the spring force is going to be up. I don't need to be juggling all the pluses and minuses of, okay, the equation has a minus and the y-axis is up plus and the change in length here would be negative. I mean, you could do it, but it's not an effort you need unless you're building a computer program to do all of these steps for you 100 times. We only need to do this a few times. So if we get magnitude from the math and direction from the diagram, we'll find we get the answer very neatly. And honestly, diagrams are extremely useful for all this stuff anyway. Friction is why we're not living in a constant non-stop pinball universe of everything bouncing off each other. So that's pretty good. Why do we need it? Well, think about it. If we had a block sitting on a perfectly smooth surface with no friction, if we gave it even the tiniest little push to the right, then by Newton's law, it would accelerate to the right and it would just scoot off and never ever stop. Nothing would ever stop. Everything would be going round and round in the biggest multi-ball imaginable. But we know that doesn't happen. The reason it doesn't happen is friction. Friction happens between two surfaces, like between that block and the surface, and friction always opposes the intended motion. What that means, if the block is moving to the right, the friction will be to the left. We say intended because if the block even tries to move to the right, there'll still be some friction to the left stopping it. That's why if you've got a big fridge there and I just stand there and try to push it, it doesn't even start to move because there is friction opposing that. And that makes sense because whenever you think, oh, why doesn't the fridge move if I push on it? Because it's very heavy. But the weight is vertical. It's down. That couldn't stop me pushing it sideways. So it's actually the friction that does that. And there's a couple of little keywords and equations about friction we want to look at. The first is there's two types of friction, static and kinetic. And there's a little misunderstanding that you would very understandably have because of those words. You'd think static was not moving and kinetic was moving. Not exactly. Static is not slipping. and kinetic is where the surfaces are slipping. So the most common example of that, static, is, well, it's me and that fridge again. The fridge isn't moving, but because I try to move it, the intended motion is to the right. The friction opposes that. Kinetic friction is where things are moving. So for example, if you're dragging a sled across the surface, let's see, head, antlers, and a red nose for the reindeer. Ooh, very mutant looking thing. But anyway, so if that thing is already moving and being pulled to the right, the friction will oppose that to the left. So that's the classic static and kinetic. But the key to not slipping is there are some moving objects that experience static friction, and they're very common examples, so we need to know them. The first and most famous is the wheel, a very famous machine. If you have the wheel of your car and you want to drive off forward in the morning, you start that wheel moving forward, so it rotates. So you can see that means the bottom of the wheel is trying to move to the left compared to the ground. And it's the force of friction opposing that between the wheel and the ground that pushes you forward. And that is a static friction. In fact, in our guts, we already know that that was always static friction, because is it a good thing when the wheels slide and slip on a car? No, it's an extremely bad thing. The point of contact with the ground is actually not slipping, so you get static friction. Another example is conveyor belts. If you have a conveyor belt carrying a block forward, so you've got a block there, and the conveyor is pulling that way, so it's trying to pull the block forward. Well, what's the only force that can do that? Well, you think about it. You think, well, would the conveyor belt work if it was perfectly smooth? No. In fact, conveyor belts are made out of materials like a sort of tacky rubber to be as frictional as possible. So it's actually the friction that pulls forward. And that could be either static or kinetic, depending on whether the block is slipping or not. So remember, the key word isn't whether something is moving or not, it's whether it's slipping or not. If it's not slipping, then the friction is static. If it is slipping, then the friction is kinetic. Yes, kinetic. Looks like a new dance album. Now, why does it matter? Because the two of them have different equations and coefficients. So we'll look at static friction first. The static friction is less than or equal to the coefficient of static friction times the normal force. Now remember, we saw the normal force a moment ago. It's the force between the surface and an object. So that makes sense. The more the surface is pressed against the object, the greater friction can work between them. Now sometimes people look at this and go, hang on, less than or equal to, what's this about? We don't do conditional mathematics in this course. But what this means is the force can go up to this maximum value. The maximum static friction is the coefficient of static friction times the normal force. So if I go back to my fridge and I'm standing there trying to push it, if it has a maximum static frictional force of 1,000 newtons, if I push with 1 newton, it's not going to kick back with 1,000 and bounce all over the room like a pinball. That only happens in Skyrim when you try to move an object. No, it'll only push back as hard as it has to. It'll push back with 1 newton. So the sum of the forces horizontally stays 0. So that's where this less than or equal to is. It'll only be as big as it has to keep things from moving. And in that case, it's just the static friction. It's not the maximum value, it's just however much static friction you need. So in this case, the static friction is 1. If I increase my force to 100 newtons, it'll push back with 100 or whatever it needs in that situation to stop. And it'll keep matching what it needs to prevent from moving. Just a little variable, the static friction, until I hit the maximum when it is about to move or about to slip. At that point, the static friction is now equal to the maximum value. And if I push any harder than that, it will give up and finally start to slide and skid across the surface. Which brings us to kinetic friction. I've now got my fridge moving and I'm continuing to push it. Really got my shoulder and back up against it there. Now we have kinetic friction opposing me. The equation for kinetic friction is just the coefficient times the normal force. And you'll notice that doesn't have any less thans or equals to, or it doesn't depend on anything. It's just now a constant value. The static friction will be whatever value it has to be, 0 up to a maximum. But once you start slipping and sliding, it doesn't matter how fast you're going. It's always exactly the same kinetic friction until it stops you moving again. There's a couple of little facts about this. The first is the kinetic friction is usually less than or equal to the static friction. So once you start moving, you're going to keep moving. The other is that any of these coefficients must be between 0 and 1. 0 is the smallest, perfectly smooth, no friction. 1 is the maximum possible friction, and you can't go above that. So if you ever find a value, the coefficient is 2.7, that's greater than 1. What that's really telling you is that friction can't actually do this. So another little tip for this sort of problem, you'll notice all our equations for friction require the normal force. So you'll want to work that out first if you're doing one of these things as well. And we've often seen problems where you have the normal force up and the weight down. And if it's not moving vertically, then the sum of the vertical forces is 0, plus the normal force up minus the weight down is 0. So in that case, the normal force equals the weight. So that's why more massive objects are harder to move against friction. The more massive they are, the greater their weight, so the greater their normal force, and then the greater the maximum static friction before you can get it moving, and the kinetic friction once you get it moving. Also again, notice just how much easier that flows and how much more sensible it sounds rather than saying stuff like Fs less than or equal to sigma Sn, which is honestly just cheating at Scrabble because it's a load of digits and you're not even allowed to use math or Greek letters in Scrabble, although that would be fun.
I hope that was useful. There's plenty more useful videos in the playlist and even more useful exam-style practice and tips and all sorts of things in the prep sessions. So make sure you join the Prep 101 Facebook Study Hub. You'll find out about everything we're doing there when the prep sessions are on, and there's even sometimes free ones, so you don't want to miss those. Hope I'll see you there.